This is our second lecture on classification methods. In this lecture, we'll focus on the model. Remember that when we're building a classification method, there are three components: the data that we use to build the model, the actual model itself that we use to make the predictions, and then the application of what we use those predictions to accomplish. Recall that this is our setup. We have a population of meeple. We take a subsample to create a training set using probability. In that training set, we collect multiple features we want to predict, in this case, the color of the meeple, as well as features that we're going to use to make that prediction, in this case, whether they're wearing a bow tie or not. Then we build a function, f, and that function predicts whether the color of the meeple based on whether they're wearing a bow tie or not. In this lecture, we're going to be focusing on the different choices for f. So that's called the model when you're talking about a statistical or classification model. And we're going to talk about three big categories of classification models that are most commonly used in the medical literature, although there's a whole variety of different prediction methods that are being used and new ones are being developed all the time. In fact, there are entire semester and year-long classes on just the statistical and machine learning models we could use in the medical literature. So here we're just focusing on an overview of understanding the key ideas of the three main classes of models that you'll encounter when reading the medical literature: regression, decision trees, and ensembling. So we're going to start off with regression. You've seen regression before in our discussion of statistical models. And so the most commonly used model for prediction in the medical literature is probably logistic regression, where we use the log probability of having the outcome divided by the probability of not having the outcome, or the logit of the outcome, is equal to a linear function that includes an intercept and some coefficients multiplied by an exposure plus some confounders. This is the simplest model, where we use the coefficients to predict what we think the probability of a particular outcome is. So here's an example of this. This is using polygenic risk scores, mammographic density, and endogenous hormones to predict breast cancer risk. And the idea is we're going to build these variables or these features into a logistic regression model and then use those features to predict the probability of a particular outcome. So for example, when we include the polygenic risk score, we might increase the AUC, or area under the curve, from 55.9 to 60.8. Then when we add mammographic density, we might increase the AUC a little bit more. And when we combine those features, we might get an even better prediction. So the idea here is that we build regression models where we include different number of terms, and then we validate how well we think that prediction model is working. The second big class of prediction models is something called decision trees, which we haven't seen before, but are relatively straightforward to understand once they've been constructed. You've seen a decision tree at the beginning of the course when we talked about the different types of scientific or statistical questions that might be asked of a medical research paper. And the basic idea here is that we ask ourselves a series of questions, and the series of questions takes you through a flowchart, and the conclusion or the leaves of that flowchart are what the predictions are. So an example from the medical literature is this tool for assessment of pain, validation in low back pain. The basic idea is you take that training set and you construct a flowchart like this, where we're trying to make the prediction on the basis of a series of questions. So in this case, they've constructed a flowchart where first they ask the response to pinprick, then they ask the response to cold sensations, then to trophic changes, and then to itching dysynthesis and throbbing pain. And as each of these questions get answered yes or no, you follow this flowchart down to the correct categorization. So for example, if the pinprick classification sends you to the left, meaning that you said that you couldn't detect the pinprick, then you ask, can you detect cold? And if yes, you end up in category C6. Alternatively, if you can feel the pinprick, then the next thing you might ask is, do you feel painful pins and needles? And if the answer is yes, you might end up in category C8. In general, these flowcharts are constructed such that you ask a series of questions starting at the top until you conclude in one of the leaves, where the leaf tells you the prediction that is being made from the decision tree. These decision trees are widely used in medical literature because they're relatively easy to understand why the predictions are appearing in a certain way, because they're according to a series of simple questions. The final statistical modeling technique that we're going to talk about for making predictions is ensembling. And the basic idea behind ensembling is to combine multiple prediction models into a single overall prediction model. So the idea is you might fit one classification tree model, one regression model, and then a third regression or a third prediction model, say of a type that we haven't discussed here, something like random forests, combine all of those models together, and make an overall prediction. Ensemble-based approaches tend to have the highest prediction accuracy of all the possible methods that you can use. They typically win prediction competitions across many different competing teams. When they try to win at prediction competitions, they often win by ensembling different methods together. The downside of using ensembling is that they're typically much less interpretable. With that decision tree, it was very easy to understand why one prediction was made by asking a series of simple questions. With ensembling, since we're making predictions with various different models, all of them are using information in different ways, and they're all being averaged together to make one overall model, it's often difficult to understand exactly why the predictions are being made, even though they're often made very accurately. So here's an example of that application in the medical literature. So this is ensemble modeling of the public health impact of a malaria vaccine. And so the idea here is that they combine 14 different prediction methods for the public health impact of this vaccine. And for each of these different prediction methods, they have different characteristics and different parameters, and they combine all of those predictions together to get one final prediction of the impact of the vaccine. So this is a highly accurate prediction of the impact, but it's very difficult to understand for any given change in one of these variables why that's making a change in the prediction, because you have to follow each of these different 14 models and understand what's happening in each of these 14 different models to understand why that prediction is being made. So we've covered the major classes here of the different prediction methods that can be used to build a classification model. And next we're going to focus on what's the application, how are those predictions used in